For this video, we will look at using the Bernoulli equation, then at the end apply the Bernoulli equation for a Pitot tube and derive essentially a handy equation that we can use on our exam. So we know here the first thing we're going to do is just practice real quick using the Bernoulli. We're told we have a tank open to the atmosphere at the top and it has a small hole at the bottom where water is discharged. So we have this tank, it's open to the atmosphere, and it has a hole at the bottom where water comes out at some velocity. So we're told here, if the water level is h measured from the bottom of the tank, the equation for the speed of water v is what? What's the equation for the velocity? If this is h from the bottom of the tank all the way to the top water surface, what's the equation for the velocity? And we're given certain answer choices. We have to pick the right equation for the velocity exiting at the bottom. So what do we do here? We know we can use the Bernoulli equation. So what I'm going to do is say this is going to be my point 1. I'm going to take the Bernoulli equation from point 1 at the top water surface. Then we're going to take it at the exit where the water exits here. So I chose the top water surface because we know we can eliminate a lot of terms, right? We can eliminate the pressure, we can eliminate the velocity there because we have water that's stagnant. Essentially the velocity is 0 at point 1, and so that helps us a lot. And here I chose 2 because I know that at the exit where the velocity is exiting is the point that I'm concerned with. So we chose from 1 to 2, and specifically we picked 2 as our second point because this is where we want to find the velocity, the speed of the water. We want to find the equation for that. So we know we're applying the Bernoulli equation from 1 to 2, from point 1 to point 2. So on the left side I'm going to have 1, and on the right side I'm going to have 2. So we know on the left side we take the pressure of 1 divided by the unit weight of water plus the velocity head, which is v1 squared divided by 2g, plus the static head, the elevation head here, which is going to be the z. We're going to call it z1. So that's for 1. That's for point 1. Now we do the same for point 2, which is on the right side of the equal sign. We have to respect the equal sign and put it on the right side. So now we're looking at point 2. You do the same thing. We have P2 over gamma. Then we have v2 squared over 2g plus z2. So now we begin eliminating essentially what's 0. So we know at point 1 the pressure is atmospheric, right? So here we're exposed to the atmosphere. So this is our atmosphere. We're exposed to the atmosphere because we have a cut here. We have essentially a hole. If we did not have a hole, we would have air. So we have to consider the pressure for air. But we do indeed have a hole. So we're exposed to the atmosphere. So the very top water surface, the pressure is atmospheric pressure. So P atmospheric equals P gauge is going to be 0. So we're concerned with the gauge pressure. So atmospheric pressure is 0 gauge pressure. So we know here that P1 is 0. That makes this whole term 0. So the velocity, what's the velocity at the top? Point 1. We know here it's just stagnant water. You can picture a pool. The water is not moving. So the velocity is 0 at the top here. And we know Z1 is going to depend on where we place the datum. So I'm going to say the datum is going to be the, essentially here. This is our datum. And we're going to say that it's obviously going to be very close to the height. So we're going to assume that the datum hits the bottom surface here. So we're assuming that in this case. But we know that Z1 will be the height above the datum. Essentially, the datum is the reference frame that we're measuring from. Anything up from the datum is positive. Anything down is negative. Anything down is negative. So we know here point 1 from the datum, we start at the datum, we go up h, right? So that's going to be our z1. That's going to be the elevation. So we know here that this z1 is going to be h. So now let's focus on 2, right, on the right side. So what's the pressure at 2? We know it's atmospheric because we're exposed to the atmosphere here. So the pressure at 2 is going to be 0 gauge, so it's 0. It's atmospheric pressure, which is 0 gauge. Now, what's the velocity at 2? We know we do have some velocity, and this is the velocity that we want to determine. The velocity at point 2 is the velocity here. So this is v2. So we have some velocity exiting at the bottom. So this is not 0. But what's z? What's z2? So we stated that the datum is here. We know we're not going up or down. So we hit the datum at point 2. So here at 2, the elevation is 0 because we're not up or down. We're directly on the line of the datum. So here z2 is 0. So now we can solve for the velocity at 2. So on the left side we have h, which is going to be this, equals to the velocity squared divided by 2g. Now we solve for the velocity, multiply 2g by both sides, and we have essentially this 2gh. Now we take the square root of both sides, and you can solve for the velocity equals the square root of 2gh. So here, this is our velocity exiting at the bottom, so our correct answer is C. So now let's apply what we just did to a pitot tube. So we know this is a flow measurement instrument, and in this case what's happening is we place this pitot tube in a channel, so the water's flowing this way. We place it in a channel, the velocity comes in this way at some velocity, then it raises this height. And this is what a pitot tube here. So we can correspond the height to a velocity, or we can correspond the entering velocity to some height. And at the end, we're going to essentially solve for the velocity at a height of 16 centimeters. So at this height, what's the velocity here? So we know that we have a pitot tube is placed in an open channel to measure the velocity as shown. If the height is 16 centimeters, so this h is 16 centimeters, the velocity in meter per second is most nearly what? So what we're going to do here is derive an equation, and I'm going to propose to you that the equation at the end that we derive is going to be the same as this one. So let's prove that. We're just going to use Bernoulli. But here, we do not take the 2 points like that, or this point and this point. What we have to do is look at the streamline where the velocity is entering. So it's entering here, and we're going to take a point here. This is going to be our point 1, and point 2 is going to be right at the mouth of the pitot tube. So it's going to be here. This is point 2. And point 2 we know is going to have some stagnation pressure, and we know at point 2 the velocity is 0. This is the stagnation, so velocity here is 0. So in the Bernoulli equation, we have to denote that. So we know we're taking the Bernoulli from 1 to 2. So we apply the Bernoulli equation from 1 to 2. So what we do here is the pressure at 1 over gamma. Here is just gamma for water, plus the velocity 1 squared divided by 2g. So we're looking at 0.1 plus z1 equals to the pressure 2 over gamma plus v2 squared divided by 2g plus z2. So here let's place our datum real quick. I'm going to say the datum, the easiest point to place it here is going to be this one. So this is the reference point that we're measuring the elevation from. This is our datum. It's directly in line with 1 and 2, point 1 and point 2. So now we know, let me just quickly denote what's the pressure at 1 and what's the pressure at 2. We know the pressure at 1 is going to equal what? It's always going to be gamma times h. It's always going to be the unit weight of the fluid or liquid we're looking at times the height from the free water surface. So here it's going to be gamma times h. But what's the height here? It's not this h. It's going to be some h value from the top. And I'll denote this in green. From the top water surface to point 1 it's going to be some h value, and I'll use lowercase h. It's different than this h, so that's important. It's from this water surface to point 1, and that's going to be the pressure at 1. It's gamma times h. So now what's the pressure at 2? It's going to be gamma times some height. So what's the height here? We're looking at point 2, right? And we realize there's fluid in this tube. So what we have to concern ourselves with is this h and this h. So we take uppercase h plus lowercase h. This height plus this height to point 2, because the fluid is inside the tube, right? So we have to do lowercase h plus the uppercase h for the pressure at 2. So now we have the pressure at 1, pressure at 2. Let's plug those in the Bernoulli equation here. So we do gamma times h over gamma plus the velocity 1 squared divided by 2g. So we know we're at 1, we have some velocity, so this is not 0. So we have the v1 squared divided by 2g plus z1. So what's z1 here? Are we above or below the datum? We're not, because we're strictly in line with the datum at point 1. So z here is 0. So we can just eliminate that, right? So we do not have any elevation difference there. So now let's put the equal sign. The pressure at 2, we denote it, it's gamma times h, but we have lowercase h plus uppercase h. So the pressure there is gamma times lowercase h plus uppercase h. And we divide that by gamma, which is this. Then we have v2 squared divided by 2g. So here, we're at point 2 now, and we know at point 2, at the mouth, we have a stagnation pressure, and that means the velocity is 0. So always, the velocity right at the mouth here is 0 at point 2. So here, this velocity is 0, it makes this whole thing become 0. So this is eliminated from the Bernoulli equation once we reduce it. And what's z2? Also, we know z2 hits the datum, so we have no elevation difference there. So this is 0. So what we have here, essentially reduced, is just that. So now we can cancel out the gammas. So these go away, and let me just reduce this further. So we have h, you still keep that h, plus v1 squared divided by 2g equals to this h plus uppercase h, right? Plus uppercase h. So we know here h is on both sides, these cancel. Then we can reduce this further, so it's v1 squared divided by 2g equals uppercase h. We're solving for velocity, so we multiply both sides by 2g, cancel. Then at the end, we have velocity 1 squared equals h 2g. Then you take the square root of the both sides to cancel the squared. So the velocity 1 equals the square root, I'm just going to write 2gh, right? What we have here. So now we have the equation for the velocity. We can solve for our final answer. We take 2 times 9.81 meter per second squared. And we know here h is given to be what? So this height here is given to be 16 centimeters, which is 0.16 meters. So that is 0.16 meters. And now we can solve for the velocity of 1. Let me do the math there. 2 times 9.81. And we multiply that by 0.16. And we take the square root. We get 1.77 meter per second. So this is the velocity when we have that height. That height, uppercase h, for this Pitot tube. So here we just proved that this equation is also applicable to a Pitot tube. So make sure you write this on your equation sheet and memorize it, because it's not given in that FE handbook, reference handbook. So we just derived it using the Bernoulli equation, and we also notice that it relates to this equation, right? Given the following condition. So that's all for this video. Thank you, and please subscribe and like. Take care.